we are so last time we got stuck at a place, and I was convinced that the proof in that book was wrong, thanks to Pratik. But now I'm convinced that it was correct. So let's just work it out again. So first of all, we'll let me. So this is lecture 9, I suppose. So so we are back at the same proof. Let's just recall that bipartite graph is a, so you can partition the vertex set into two parts, and every edge has one vertex in x and another and the other in y. So we're always talking about simple graphs, and that means no loops or multiple edges. And we're talking about finite graphs. So the vertex set and the edge set are both finite. Okay, and we had this notation, let A belongs to V, then gamma of A, and this is where we went wrong first. This is the set of vertices of uh, G incident with A. So A is a thing, and then we have gamma of A, which is union of gamma of A, where A belongs to A. So here A is a subset of B. Then we have the incident things. And we had a matching. M is a subset of E such that no vertex is incident with more than one edge in M. And we had a theorem. This is Hall's theorem. Necessary and sufficient condition for a complete matching from X to Y is that for every A belonging to X, gamma of A has to have more number. And recall that complete means all vertices in X are covered. So proof, we got stuck at some place. I'll just redo the proof, but first of all, just recall that this side was very obvious. This was okay. This was obvious. So if there is a complete matching, then if you just take the elements in that matching, that itself will be bigger than equal to A, right? So this side is obvious. This was the side where we got stuck on. And I think, I hope you remember vaguely what the proof was, but let me work out what I thought was I'll work out an example, and we will do, we'll go through the whole thing, and then maybe the proof will be easier to understand. So let's do an example. So the proof was uh, this was computational actually. So let's work through the complete computation. So let's work through this example. So let me. So I made some example which was highlighting one point. So this is, let's say this is the vertex x, and this is the vertex at y, and these numbers don't need to be equal, but let's say this is the proof. This is the ground. So 3 goes to BCB. Okay, so what we do is uh, we begin with some matching. So begin with, so what we are going to do is we are going to have we are going to run through, well, why am I writing it right? We will run through an algorithm to generate a maximum matching, complete matching. And then the proof basically is a piece of this guy essentially. So we begin with one red egg. So we begin with uh, so the matching step one. We begin with some matching. So let's say the first matching is take one edge, 4C. So something in a matching is a red edge. And then we start with, so this is 1, 2, 3, 4, 5, A, B, C. Okay, so I have a tendency to erase, but so we begin with some matching. So there's a matching which is basically 4C. Okay, and then we pick a vertex x0 which is not in this matching, not in. So this is x, this is y. So the goal is to get a bigger one. Goal is get a bigger one. Okay, so let x0 be 1. So x0 is 1, and we want to pick one more guy, some y1. So all he's saying is that if x0 is there, then there has to be some vertex on this side which is attached to 1. So pick that as y1. So let's choose y1 to be a. Y1 to be a. Okay, so all I do is I go from here to here and it's a blue edge. Now, if the algorithm says if this guy has a red edge attached to it, you go and find an X1 over here. But nothing, this one has not got any red edge attached to it. The only red edge here is between 4 and C. So this has got nothing attached to a red edge. So then this is it, and what we do is we change this blue to red. So we get, in step 2, we get 1, 2, 3, 4, 5, 1, 2, 5. So we get this matching. This is the matching. Okay, now we run the program again. So we say, okay, pick one more x0, pick an x0 which is not in this matching. Let's pick 2. So let's pick x equal to 2. And then from 2, we have to find one y1 which is on the other side. Okay. So we can go either, there's only one possibility, we can go to B. So y1 is equal to B. So again, you make a blue edge. So there are 2 red edges and 1 blue edge. Now this y1 has no red edge attached to it. So we found our path. A path is basically a blue and red path which is of odd length. So we convert it into red to make it red. So in step 3, so make 2B red. This is the output of this guy. So again, 1, 2, 3. At some point, it will show up something nice. That's the point we are waiting for. So now we are starting with this matching, and we again pick another. So we have, at each step, the idea is that at each step we are finding a bigger matching, right? And this whole idea of an alternating path is what we need to understand. That when we have a bipartite graph, we get an alternating path like this. Okay. So all right. So here now let's take x0 equal to 3. Go back to the original graph. Now I can choose x0 equal to y1 equal to any path which is not in the matching. So I can go from this to B again if I want. Okay. Or I can go 3 to C over here. 3 to C. So let's choose, oh, we are here. So let's choose y1 equal to C. So I've chosen this as a blue edge. Then he says x1 is, now see, now this x1 has a red edge attached to it. So you choose x1 equal to 4. Okay. And now these two guys are together linked with at least 2 vertices. And here I just have one vertex, C. So I want some other vertex other than C which is incident with 3 and 4. So some other incident other than 3 and 4, something other than C I want. So let's choose B again. Let's choose y2 equal to B. So y2 is chosen as B. Okay. And now again we say B, is it linked with the red one? Yes, it is linked with red one. And now you have x2 equal to 2. So follow the red guy and you reach x2 equal to 2. Now again you see, can we do something with 2? Well, we can't do anything with 2, but what we are saying is one of these 3, 4, 2 is connected with something outside. So 2 is not connected with anything outside of this. Uh, 3 is connected. 4 is connected. So let's go to 4 going to E. Let's go y3 equal to E. So these three guys are connected with at least 3 people outside, 3 other vertices. So we choose one of them, which is not. So here it is. So we choose this E. Okay. So where are we? X2. So now E is linked with a blue edge over here. E is linked with a blue edge to 4. This is where we got the 4. Now how do we get, and further E is not linked with anything else, any other red. So we stop here. And now how do we find the path? So the path is you start with the last guy, E. So you start with E, go back to 4, go back to C. So you go this is connected with a blue edge, then a red edge, and then with a blue edge. Right? And we've reached 3. We've reached X0. Somehow we've reached 3 and we stop. So this is the guy, this chap is the path which the um, algorithm gives, and we change it, make this blue and make this red. So this is what we get. So step 4, we have 1, 2, 3, 4, 5. This is a red edge. This stays a red edge. Now this one becomes a red edge. This I delete, and this one becomes a red. And then, so this is where we get. So M becomes this guy. 1A, 2B, 3C, and 4E. So this is a key step which we were getting confused about, I think. Anyway, so now what is X0? X0 is 5. X0 is 5. And we find one more thing, which is X0 is attached to something. X0 is attached to E. So Y1 is E. E is attached to 4, which is red. So X1 is red, which is 4. Now 4 has to be attached to something else, whatever, maybe D. So 4 is attached to D. D is not attached to any red line, so this stops. So we've got this path over here, and now we change M over here, and we get so M becomes 1A, 2B, 3C, 4D, and 5, and we are done. So we get this. This is the output. We get a answer. So at each, this is the idea of the proof, that each step something or the other matches, and this is a critical thing. This is a critical point, that all these guys together lead to something new, and then you start with wherever you stopped, you start back and you get to the path which you require. Okay, any questions on this example?
Professor, just a small question. So, a complete matching is a concept for a bipartite graph, right?
No. Complete matching can be for anything. Um,
So, Professor, like when we say in a complete matching, all vertices in X are X are covered, then what is our X here?
yeah, yeah. So I mean, okay. So this is just a remark. Um, a complete matching in a graph G is a set M of edges such that um, all vertices are of G are incident with one edge in M and two no vertex is in two uh, um, is in two edges in M and in a so this is in a graph. So what we are doing is a complete so in a bipartite match, bipartite graph, a complete I mean it's a little confusing matching from so v equal to x union y from x to y is when all vertices in x are in M. So y may be left. I mean, there may be something missing in y here. Um, so a simple example of a let's say this guy. So there are four vertices, and this is a matching. This is a complete matching.
So, Professor, in like if you consider an entire graph and if you consider the complete matching on the graph, if a like a necessary condition for a complete matching to exist would be having an even number of vertices, right?
Yes,
And Professor, just one last thing. So, our theorem is specifically for bipartite graphs.
exactly. Yes.
Okay. Thank you, Professor.
So this theorem is for bipartite graphs where this nice algorithm exists. So actually tomorrow I should mention tomorrow there is a seminar by Nishad Kothari on graph theory, and he's talking about matchings, and he's prime. I mean that's the primary reason why I'm doing this theorem now, because I wanted you to get at least some idea what a matching is, right? So he only suggested this particular proof uh, that it has some ideas which he probably wants to utilize. Okay, so let's do the proof again in view of this example, and now let's see if your queries from yesterday are addressed from last time addressed. This is fine. I mean, so far this is okay. So I should mention then there's a perfect matching also in a bipartite graph. And this is when x is equal to y. So the number of vertices is so in a this is a well actually I think this would be called a perfect match. Let me I'm not so sure about this now. Let's call it a perfect match. So complete matching here x to y and then perfect matching. This makes more sense I think. So let me check. So to check. whether this whatever I've said is a this thing. So this is I think this is called a perfect match with two n vertices. And in a bipartite graph, uh, we can do this. This is not bipartite, by the way, this graph. So bipartite graphs are a lot simpler. Okay, anyway, so back to the proof. We assume this way. We assume gamma of A is bigger than equal to A, and for every A belonging to X, right? Let capital X be N, M is less than N, and suppose there is a matching. So this I actually wrote yesterday, so you don't have to rewrite, just read it. Suppose there is a matching with M edges. Okay, um, we show a matching with more than M edges. So then we can iterate and then go on. So let edges in M be all red. Okay, and let x naught be a vertex in X which is not incident with a matching with the edge. Okay. So the claim again is there is a simple path of odd length starts with x0 uh, with alternating blue and red edges, and terminates with a blue edge, and a vertex y in Y which is not incident edge in Y. Okay, so again, if we find such a path, we are done. Just replace all reds in this path by blue and vice versa. So we get one more red edge than earlier. I mean, this is simply saying that if we have a blue here, you know, red here, then blue, I'll just mark it like this. Right? Then if it's an odd length, then there's a even number of there's a less than half uh, number of red edges, and you interchange them. So this is going to be one less. So this gets converted, interchange red and blue. So so there is an x naught. So let x naught be a vertex not incident with any edge in M. And why is this there? Because M is less than N. So number of edges, number of vertices incident are less, so there has to be something. And let y1 be a vertex in Y incident with x0. Okay, so x is not in M, so the x0 y1 is a blue edge. Since x0 is not incident with any edge in M, right? So if y1 is not incident with any edge um, in M, then stop. And we found the path. That's okay. Else there is an x1 in X such that x1 y1 is in M. Okay. Now gamma of x0 x1 is more than 2, so there is uh, a vertex y1 incident with x0 or x1. Again, um, you know, attach a blue edge to this one, to this edge. And again, iterate. Y1 is not linked with uh, red edge, stop. Else continue. So carry on this process, and we get a sequence of vertices x0, x1, xk, and y1, y2, and yk. And then again, let's say we've gone on this far, then we uh, uh, check if yk is incident with a red edge. If not, stop. And if yes, there is an x k plus 1. So now I think the query which was there uh, was that what if this xk plus 1 was one of these guys? So this is where we were, that we were here actually. So we have x0, x1, x2, and so on, xk, and y1, y2, y3, yk, and we're saying, so the thing is that these were all red, right? So the point is that YK was not part of the red one. YK had come from a blue thing from somewhere. YK had come from somewhere with a blue. And YK, if there is a red thing, it has to be different from these guys because this was already part of the matching. And X0 we started with something which was not part of the matching. That's why, that is where I got confused last time. That we have to have an XK1 here or not at all. Okay, now, so is that clear now? I think Pritam has left, so should maybe he's figured it out in any case. Okay, so once it stops, once the process stops, okay, how do we get the power? Say at yk plus 1, here is how we get the path. So start with yk plus 1. It is incident with a blue edge, let's say I1, okay, in x0 to xk. Then xi1 um, is linked with a, so we are at yk and you go to blue. This is linked with uh, a red edge, yi1, and that is incident again with the blue edge. So this is yi1 is incident with the blue edge, xi2, and so on, and go on until you reach x0. So basically what is happening is that, there could be a multiple guy. This guy could go with some other chap also, but somehow eventually we will reach x0. And then you've got the path. So this generates the path. And we're done. So yeah, I mean this interchanging paths argument is a very clever argument, as we can see, and it's very useful technique. So graph theory is full of such clever arguments. Okay, any questions so far? Any questions so far? So as a corollary, we have a finite regular graph, regular bipartite graph, sorry. Has a perfect match.
So, Professor, what is a regular graph?
Yeah, regular is all vertices have same degrees. And perfect matching we already saw. Um, every vertex is, has a uh, uh, is in the match, is incident with some edge in the match. So regular, suppose regular is of regular means what? If it's regular, then x is equal to y. Why? Because number of edges uh, is going to be, let's say regular means is let's say d times x, where d is the degree of vertex. So how many edges are going to be there? Each guy has got d vertices coming out, d edges coming out, and they're going somewhere. So this is the number of edges, and similarly, this is true. So it has to be the other side also. So this implies that x is equal to y, and then one can then Hall's condition is trivial too, because the number of edges in gamma A is going to d times A, which is going to be bigger than A for any A. So this is a very interesting thing, that if you have so I mean basically what it's saying is that if you go to a dance and every girl likes agrees to dance with three people exactly, then everybody can find a partner. That's what it's saying. I mean, of course, with one it's possible, and with any D, if it's regular, then it's okay. All right. So, any questions so far? So it's a complicated proof. So it took us a while to process. I remember this proof a lot from my PhD days. So that's why I wanted to go over it again. Looks like I got confused. Okay, any questions? So here's another formulation. By the way, just a question. Uh, how many mathematicians do you think? I mean, if you leave out the physicists, how many mathematicians have won the Nobel Prize? You know the
Can
answer?
we consider Nash?
Huh?
Can we consider Nash?
Yeah, Nash is yeah. So the only people other than the physicists who have won, who mathematicians, one could consider them to be mathematicians, and who have won are Nash. So they have won for economics, right? So Nash is one, and then there is a more recent couple called Gale and Shapley, and actually they work on this stable marriage problem. So this these are the other two mathematicians who won the Nobel. They sneaked it. I mean, they sneaked in by uh, doing it. I mean, their work was used in economics, but they're essentially mathematicians, and they're working on this stable matching problem, which is related to this marriage problem, which I've been describing. So it's a mild extension. So anyway, another formulation is let A1 A n be subsets of a finite set S. Then AI for I going from 1 to n form a system of distinct representatives or an SDR if AI belongs to AI and the AIs are distinct. Okay, so Hall's condition for any subset J of S or Yn, mm, the number of elements in I belonging to J should be bigger than equal to J. And if and only if A1, A2, AN have an SDR. So this is known as Hall's condition, which is essentially what we did earlier. Okay. So well, let me. So essentially, what we are saying is that we have, let's say, um, A1, A2 over here and A1, A2 over here. And this is by inclusion. And the number of elements in, is it? Um, so am I doing the other way around? Hmm. Does that make sense or no? So I'm picking out one, or it's the other way around.
So what is an SDR? What does an SDR mean?
SDR means system of distinct representatives. So I'm confused whether these should come on this side on. So if you have, let's say, A1 equal to 1, 2, 3, A2 equal to 2, 3, 4, and A3 equal to 1, 4. So what I would like to do is that I would like to have one element from here which is not which is unique to this guy. I mean, a distinct representative. So I would like maybe if I put if I choose 1 here and 4 here and 2 here, that's a system of distinct. So this belongs to this belongs to this belongs to this.
Okay, so they don't have to be distinct to the superset, but just distinct from each other.
Yes, yes. So AI, small AIs are distinct, and each one belongs to this guy.
Okay.
So it's like, I mean, you have clubs here. These are clubs. Um, so these are clubs, let's say, and these are uh, club representatives.
Yeah, then
So
maybe the other way around works because A1 will be connected to 1, 2, and 3.
yeah, yeah, I think that's you're right. Well, we want gamma of A, right, to be bigger than J. So, I mean, the earlier guy was gamma of A is bigger than equal to A. So gamma of A comes this side. I think, yeah, I think I was okay. A1, A2 here, and then I've got inclusion. So I mean, this was from our previous theorem, and this is A1, A2, A3. So if you take any subset here and take these guys, their numbers should be more than these numbers. Yeah, this is fine. So this is okay. This is included. I think it's okay.
I'm a little confused. I think I didn't get that.
Um, in the previous theorem we had this x and y, right?
Yeah.
And then we had this these guys over here, and A was a subset of these vertices,
Right. Yeah.
and gamma A was the guys here, which are incident, and this was our condition.
Right.
So here it makes sense that you want gamma of A means union of AIs, means all these guys together. Isn't it?
Um,
Or the other way around.
I'm just trying to think of it from the previous problem. So we have the sets A on the left side and the elements on the right side. Then you can find a matching for each set to a specific element.
Yeah, that's the other way of looking at it. Okay, maybe you're right. Okay, so what he's saying is
And since J is all, we're taking any subset J, so shouldn't
this
that
is
be any
A1,
subset on the left
A2,
side?
and so on. And then any guy here. And this is by inclusion, right? So if A1 contains more than these guys, then that's it. Okay. Yeah, yeah, makes sense. Basically, we want that. How is this condition happening? So J is any subset of,
Of the left side, any set of A's,
yeah.
and gamma of those will be all the elements in them.
So J is any subset. Okay. Yeah, I mean, if this union is always more than this number, then we can pick one basically.
Yeah, yeah.
Okay. All right. So I'll say, yeah, what should I say? It's okay. Okay, so one more formulation. This is Kinnick's or Koenig's theorem. This is also a formal. It's a so. I mean, this was. Um, I would say first of all, I should say that this guy wrote the first book on graph theory, and this was in 1936. So before that, graph theory existed, but only in a few works. I mean, nothing systematically was done. And uh, here is this is another formulation, but I mean, a lot of these formulations they look very different, but they are sort of equivalent and can be derived from one another. And I might give a couple in the homeworks just to get a handle of it. So this is let A be a 0, 1 matrix with entries let's say Aij. Um, a line is a row or a column. Okay. Um, and the theorem is, I mean, one formulation of this theorem is that the minimum number of lines required um, containing all the ones in A is equal to uh, the maximum number of ones in A, uh, no two in one row or column. Okay, you know, let me just first give you
Professor,
an example. Yeah,
what is its maximum numbers of ones in A, and what's after that?
no two in one row or column. So kind of independent ones and K's. So here, this one, like these two are, this is a line, this is a line which covers all the ones. And these these two ones are the ones which are no two in one line. So let's do another one. 1 0 0 1 0 0 1 1 0. So these two are the lines here and here. This is the minimum number. I mean, you could have these lines also, but there are three lines, right? So the minimum number of lines required is two, and the maximum number of ones, no two in a straight in one row or column are two. I mean, these two can't happen. These two cannot happen. So either this and this, or this or this. That's it. You get what the theorem is saying?
Yes, Professor.
So there are these. There's a bunch of min-max theorems. There are 10, 15 of them, and all of them keep showing up all over the place. And all of them are extremely, clever. Can be derived from one to the other, and so on. It's a nice game to get that. It's a bit, I would say. I mean, this area has become a bit old-fashioned, but I mean, with Gale and Shapley and all that happening, so it doesn't really. There are people who are working on it. It's very attractive area of combinatorics. Number of ones, no two on a line.
Oh, Professor, this is also just it will also just be equal to the rank of A, right?
Yes, yes, right. So I mean, for the 0 1 matrix for sure. So clearly, m bigger than equal to m, right? And uh, let the minimum covering consists of r rows and s columns. And without loss of generality, suppose they come on the top left of the matrix. So what we want is that you have this matrix and there is this minimum rows and columns containing all the ones. So all the ones come here, 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 and here there is just a zero. There is nothing here. Okay, fine. This part is fine. So all the ones are here or whatever, right? And we define AI to be um, all the j's bigger than s such that aij is equal to 1. So what are we saying? These rows are 1, 2 up till s, and for I equal to 1, 2, 3 up till r. So this is 1, 2 up till r. I'm defining all the columns, all the j's where there is a 1. So this one, and so on. Okay. So you understand the definition of AIs? It's just this part we are taking in each, for each row, we find all the columns where there is a 1. Okay. So if some k tuple of AIs contains less than k elements, then we can cover all the ones in these rows by um, k minus 1 columns. This is impossible. Let me write it down before I figure out what I've written. Since m is minimum. So what he's saying is, suppose some k tuple, suppose these k tuple, these two guys contain less than k elements. So suppose there are less than there are three of them, and A1, A2, A3, and they have less than three elements, maybe two elements. Then I can cover these guys over here. I can cover with, you know, uh, two columns, right? So then I can shift these over here, and these rows are anyway being covered, so I can reduce the number of r plus s. R plus s is the minimum. You get what I'm saying? So if I can cover any k of these guys over here, any k of these rows, I can cover with less than uh, you know uh, k columns, then I can move them here and I get a contradiction to this r plus s being the minimum. Is that okay? So so basically this means that Hall's condition is satisfied. And thus they have a SDR. So these guys have an SDR. Therefore, there are R1s, node 2 in a row, right? No two in the same line in the first R rows of this matrix. What do we call the matrix? Nothing. And by a same argument, we can get S once node 2 in the same column uh, in this part. This part. So we can run the same argument here and make B1, B2, Bs, and then again we can find these. So that's it. So then we found it. So we got exactly R plus S of these columns here and rows here, which cover everything. So very, very interesting that here we have got these lines which are like this and this, and these guys are the blank areas are where I'm finding the independent sets. So anyway, this shows that thus M is going to be bigger than R plus S, which is equal to M. So this shows M is equal to M. So we'd already shown that small m was bigger than M. That was clear. And we are done. Okay, in terms of graphs, so Kinnick's theorem is as follows. Um, there's some definitions. So again, there are lots of definitions in graph theory. Once you get confusing, a vertex cover in a graph is a set of vertices that includes any uh, that includes at least one endpoint on each edge. A vertex cover is minimal if no other vertex cover has fewer vertices. And the theorem is again unique, unique restated. Let G be a finite bipartite graph number of edges in a maximal matching equals the number of vertices in a minimal vertex cover. So this is kind of another. I mean, it's a remarkable restatement. I mean, you have of course finite bipartite graph, but one it's relating something about edges with something um, about this thing. So about vertices. So I mean the way to translate it is as follows. So um, suppose you have x and y. So same thing, one, two, three. Suppose x and y are the two sets and they're bipartite, and you put a one if there is an edge between this and this. So let's say there's an edge here and there's an edge here. So this graph is 1, 2, 3 and 1, 2, let's say, and you have an edge here. You have an edge 2 going to 2 and 3 going to 2. This is a bipartite graph. And you want to do a minimal cover, and a minimal cover would be something like uh, a maximum matching would a minimal cover would correspond to, I think, the line, right? So line is a vertex covering. If I put a line here, for example, this is a line and this is a line. Then what's this saying? Then suppose I put this is a vertex covering, and a matching is um, um, matching is an independent set here. So let's say this is a match. So 1 1 is a matching and 2 1 is a matching. 2 2 is a matching. This is a matching. Um, One's more 2 in a line. So this is just a restatement of the previous stats. Okay, any questions? Any questions? So there is another object which is which is very related. I mean, at some point I'm going to do some network theorem too because I think that is important. But that'll take much longer. But I just want to highlight. So there is a concept of a Latin square. So what is a Latin square? So first of all, an m by n Latin rectangle is a m by n matrix. So a lot of these things came from recreational math, MIJ, whose entries are integers, and they satisfying 1. So all the numbers between 1 and n are here, and no two entries in any row and column are equal. Okay, so let's and a Latin square is a full. Uh, I mean, it's a n cross n Latin rectangle. So as an example, you have 1, 2, 3, then you can't have 2, 1, 3 here because this 3, this is not allowed. But you can have 1, 2, 3, 2, 3, 1, 3, 1, 2. This is okay. This one. So how much time we have? Well, let me state a theorem and I'll indicate the proof. Let M be an uh, M cross N Latin rectangle with n less than m, then M can be extended to a Latin square by the addition of n minus m rows. Let's just do an example how one would go about it. So suppose I've got 1, 2, 3, 4. So I'm making a, this is a m equal to 1 and n equal to 4 rectangle. Now what I do is over here, the next guy, I can choose all the elements which are not uh, this one. So let's take A1 to be equal to 2, 3, 4, A2 to be equal to 1, 3, 4, A3 to be equal to 1, 2, 4, and A4 to be equal to 1, 2, 3. So what I want over here is I want a system of distinct representatives from here, right? And so for example, I can choose 2 from here, then I can choose 3 from here, and I can choose 4 from here, and I can choose 1 from here. So I've chosen 2, 3, 4, and 1. Now, can I choose a system of distinct representatives from here? So I choose, let's say, 3 from here. Um, I can choose 1 from here. I can choose 2 from here. And then, well, then I get into trouble. So I can't choose 2 from here. I have to choose maybe 4 from here. And then I choose 1 here, and then I can choose 2 here. So I can choose, so cut this, 4, 1, and 2. And then there's just, I mean, you just have this left, 4, 1, 2. So I've constructed, I've extended it, and I basically use Hall's theorem, and I have a constructive proof of Hall's theorem. So I have an algorithmic proof, so I can determine, by converting it into matching, and determine it actually. So this path proof actually helps you determine this thing. I mean, once it's translated into the Hall's theorem idea. Okay, so I think I'll stop here. Maybe next time we'll do a proof of this. Again, I should mention tomorrow there's a talk by Nishad, and he has a handout on the website. So if you go to the Ashoka website and search for math seminars Ashoka. If you do a Google search, you will get to a Ashoka website. I just want to show it to you. Mm, wow. There you go. So now I can show it. Hmm. Yeah, here you go. So there is a handout over here. If you click on it, that he wants you to keep. So if you go to the math seminars site, you will find Nishad's handout. Okay, any questions? Okay, then I'll see you on Wednesday and hopefully even tomorrow.
Thanks, Professor.
Okay, bye.